Hi, I'm Tom Murphy. Today I'm going to be talking about live coding, and specifically live coding in a way where we're dealing with side effects and still remaining declarative and keeping the nice pure properties we like about systems. So what is live coding? In a general sense, we're talking about running programs that the programmer or programmers are changing as the program is running. So a core operation is hot swap, which is the changing of a program, so adding pieces or fundamentally altering pieces which already are running. A simple example of this is sometimes when you're in GHCI or a REPL, you may end up doing something akin to live coding or really live coding. The sort of crucial component is that you actually are altering the program that is running, not just doing eval. Erlang and OTP offers another example of live coding, not in the arts domain, which is you're able to define and redefine functions as the system runs. So imagine you've got some function that you've written that takes user input and sends it to the database or something, and you realize partway through that there's a bug that allows some exploit. I, as the programmer, can write a new version of that function, compile it, and put it into my running server code, and the next time that function is called, the new function is called. So this is hot swap. This is a form of live coding. The other use of live coding is for art. That's why we're at Farm. And this is really sort of blossomed. It's a bit of a slow blossom, but it's really a sort of common practice now for art. And there's some really exciting things that are being done where it's both a performative process as well as a creative process. So in one sense, live coding is interesting as performance for being live coded, but it's also a way of creating music by keeping things in the air and changing them while they're happening. So imagine we want to do live coding today. Typically our two choices are either purity with limited I/O, and so there are a lot of systems. One that I really like that falls sort of into this model is called tidal cycles, where you're definitely doing live coding, but the main thing you're doing is altering data and functions. But you're not really interacting with the outside world in a sort of pervasive manner. The other choice that you have, as always, is just have a big ball of state. There are some other really great systems which use this model, but sort of fundamentally, you need to have global references. You need to, if you want to interact with the outside world, it's difficult to put restrictions beforehand on what you're able to alter because you're live coding. So I want to interact with the world, though. I like my functional purity, and I like declarative programming, but I also like MIDI instruments, and I also like outputting music. So I would like to do side effects, and I would like to do so in a way where I don't just throw up my hands and go straight to full pervasive global state. This is the only contents of this slide. Just aha, FRP. This, I think, if you walk into a room of programmers and say, you know, I want to limit my global state, but I'd really like to do a lot of side effects, I think they'll say this. So, and as an additional constraint, I'd really like to do hot swap. So I'd like to experiment, create things, alter things as they're running. So what is being declarative? What am I talking about? FMAP is a really central example. This is Haskell code. FMAP takes a functor, which is a sort of, we can say, computational context, where we take a function we take a value in that context, and we return another value, the application of that function in the same context. If we apply equals A to a list of characters, we get a list of Booleans. If we apply equals A to the context of IO character, so if we get a character from the user, we get an IO Boolean. And in pseudocode, we could represent a sort of unending stream of user characters, which I'm putting the type FRP char, which is the last key pressed. And what I would like to do is be able to apply equals A to that and get a unending stream of bools, which was the last key that I pressed, A or not. And so we still have state, we still are interacting with the world, but in some sense we have controlled state. The crucial thing is we don't have an IO ref that some other function that we're not aware of can go right to at the same time or something like this. The question is, can we do this while still having hot swap, and can we do this in a way that allows for live coding where our actions aren't predefined beforehand, where the programmer, the artist, is still allowed flexibility in what they're able to change. So in this talk, we're going to go over a couple things. One is the general semantics of an FRP system which has this operation of first-class hot swap. And second, we're going to give a more specific formulation, the midair library, both its implementation and the idioms for actually using it for art. So the core unit in midair is called signal flow. And we have data which goes from an A to a B. And so for the FRP people in the audience, this formulation, not the general semantics that we're talking about, but midair, is push-based. And what that means is we have a graph of signal flow, and it fires given inputs. And so we're not continually polling for input from the environment. If we have a signal graph that's waiting on a MIDI note from a MIDI piano, and nobody ever plays a note on that piano, the graph will never fire. This is also discrete time, which means time is discrete. It's not infinitely divisible. This is another thing which is specific to midair, but not the semantics in general. Again, for the FRP people in the crowd, if you're looking for an analogy, this is most similar to eFRP or an RTFRP, real-time and event-driven active programming. So some basic functions. We've got smap, which is a map within sflow. sfold, earlier today we looked at fold p, and this is the same thing essentially. I'm happy somebody made the observation that really it should probably be called scan p or scan, because we are going from, the analogy is you're going from a list to a list, and here you're going from a stream to a stream, but this is what it's called. So sfold takes a start value, takes a function to consume, and returns a stream. sfilter takes a stream and returns a more limited stream, which only fires when the predicate is matched. Scompose is like the dot. So B to C, A to B, we get an A to C. And so this should really look both familiar and comforting to people who like to write in this style. The goal really is to have, whether we're talking about signals which are coming in from a messy outside world, we really are able to talk in a declarative manner. There's instances for applicative and arrow, so we're able to write code like this here. So here's an actual snippet of midair code. The type of this is it takes a character like from the user and returns a bool. So we're filtering based on is this character a space, and we're passing that bool. We're ignoring it, but then we're doing not on an initial value, or the current value. And so what this ends up doing is toggling a Boolean. So each time you hit the spacebar, it toggles between true and false. The slide here says demo. I'm continuing the tradition of most of the speakers today of presenting off this laptop that was helpfully donated because the projector is sort of finicky. So you'll have to imagine it, but I think you can probably imagine.
Your filter is giving booleans or is really removing?
Oh, I'm sorry. Yeah, you're right. S-filter is returning characters. So it's taking a stream, it's taking characters in, spitting characters out, but it's only spitting out the space characters. Right, that's a good point. Yeah, so unfortunately for this slide, I'm going to be doing some demo later on, but for this slide, you'll just have to imagine me hitting a space bar and the words true and false showing up. I think it's not worth the effort to get that working. So it's also applicative, so we can do nice things like given a signal flow from x to double and an x to double, we can multiply them in a way that's very nice. And note that this is deterministic, so there's this will always fire the same way. We don't have like race conditions or anything like that. Even if, again, this is coming from the outside world. Question?
So if you were filtering two lists and
yeah.
multiplying them together, but different elements were removed from each, would it be the things at the same time, or would it just line up the resulting lists?
Sure, that's a...
You might have something from way in the past or something from way in the future.
Right, that's a very good question. So the way that the question was, if we have two things which are being combined and one of them has been filtered, what happens when the other has not been filtered? So we have one fire but not another. The way the semantics works here is we keep, so that is considered a fire. We take the existing value. So signals, the way we consider them are their values which fire when they change. They fire when they fire. We are notified when they fire, but they have a value at every point in time. But they may only be observed at a fire of something.
They're actually, so the signal of type A is actually, in fact, a signal of type maybe A. So that sometimes it's nothing. Would it be
No. So. So no, it's not a maybe you'll never. If one has fired and another, so if we, like for this example here, if width has never fired, then area also has never fired. So.
That would be what it means, because then you have the maybe on both arguments and you collapse it, and if one is nothing, then the other one is also nothing.
So when you fire, that gets stored and then the next time height fires, you multiply them together? Is that right?
Yes. So as soon as there is a value for both, then then it's computed.
Yeah. So the semantics is step functions.
Right. So there is not necessarily an initial value. For many of them, like for example, S-fold, we have an initial value, but it is possible. So these are infinite into the future, but they're not necessarily starting from time zero.
So S-fold fires at time zero.
That's actually, to be honest, I am not positive. Let me think about that for 1 second.
Perhaps you can keep on.
Yeah, maybe it is worth talking about after. Yeah, but I'd be happy to talk about that in the questions. And then after that, I'd be happy to talk about it offline. So just like we can do applicative this way, with applicative do, we can write in a sort of nicer idiomatic style. Sorry, I'm Okay, so then we want to do hot swap. What we would like to do is make a change to how the graph is computing at any point that we think that we may want to change it. So when we talked about fold P before, we'd like to talk about folding over the past. And the question is, how much past are we talking about? I can talk about space leaks, but really the question is, if we want to change our program, are we changing what it has always meant, or are we changing what we're doing in the future? So as a simple example, imagine we get input from somewhere, so a MIDI instrument or something like that. Imagine you're turning a rotary control, you have an increment or decrement. Given an increment, we increase our volume by, we multiply by 1.01, otherwise we multiply by 0.99. If we imagine as an analogy lists instead of streams, because it's simpler to think about, if we fold L, regular fold L, over that, over our function, we end up after a little while of turning the knob with a value of 1.6, which is a reasonable increase. If we were to hot swap the naive way and say, we're folding over the past, so we need to fold over the whole past. When we change this program to be a little more responsive when we turn the knob, suddenly we've deafened everybody. And the argument that Midair makes is that this is not the right semantics for live coding. And instead what we would want to do is when there's an update to how the program runs, we're changing how the program runs in the future, not how it quote unquote should have ran. So we do actually allow each change of the rotary to have a different value change, but only in the future. I'm going to skip some of the design things because I'm a bit short on time. The only thing I want to note is for efficiency, a lot of the design decisions from Midair and live coding things in general comes from the observation that compile time is runtime for live coding. So if I'm on stage, I want to hit a musical cue and I miss it, I don't really care whether I missed it because the code was too slow to hit that cue, or whether the code didn't even start running because it was still compiling. The concern is, my takeaway from this is we need to write code which is fast even when not optimized, which actually really limits what we're able to do. For the purposes of time, I'm going to skip internals. Fire, I'm going to talk about for a second, but only a second. We keep a reference to a large signal flow graph, which is essentially we've got a GADT, which has been simplified a bit here, which says, to answer your earlier question, I think fold does fire right away. So it's essentially a tree. When we get an input, we walk the tree. We return either a value or no value, depending on whether there's been filtered out. And we do an update to the graph because potentially the graph may have altered. So far, we've only seen static graphs, though. What does this talk about? Hot swap. I introduced three sort of primitives here. First of all, we've got explicit reference to pieces of the graph. So given a piece of signal flow, I can, with make node ref, I can get an explicit node reference. And then I can go back from a node reference to signal flow. These are not inverses though. When I call nref, this signal flow that I get back still contains the reference to this particular ref. And so when I alter that ref, this signal flow, wherever it is, also is altered. Hot swap actually does that action. So I take a reference, I'm allowed to parameterize my update on the last fire, the last input and last output of the fire, and then I give the signal flow, and then it's an I/O action to update it. These can be nested, which is pretty crucial for live coding. So we can create sort of like coarser and finer granularity in our effort to update. I'd like to, I'm going to skip this for time. Idioms, we've got some nice idiomatic functions, a lot of base and prelude. These should look familiar to people. So stake returns a list of the last n elements. All returns whether every input it's ever seen has passed a predicate. So it's like all on a list. A lot of these are translations from list, or print takes does an IO. This is essentially an IO action. Takes a showable and returns a value which prints. And then we have some hot swap idioms. Hot swap hold is a pretty, if I can only talk about one, which it's looking like I probably can. Hot swap hold is sort of simplest one, which is we take a node reference and then we continue to emit the last value that it emitted. Or more specifically, we hold the value, we stop emitting, but that value is able to be used from elsewhere. So if I have turned my knob and I'm happy with the volume as it is, I can call a hold and stop emitting. So, and then I can hot swap back to something else given the last inputs and outputs of that value. And it's the last inputs that caused the last output. Demos. So I'm going to have to do a bit of showing you the code and using the code separately. So here are a couple okay, I'm going to show, I've been using the simple volume change analogy. I'm going to demonstrate that here. So I'm going to start a little piece of music going in title, and then alter, instead of the volume, it might be easier to perceive, or maybe altering the rate of playback of the samples. Hopefully this one can see that. Can everyone hear that okay? Okay. So we can see we've got a function here, change rate, which is we call make node ref. So we have a simple thing here. We start at 1. We've got a folder. We start at 1, and we call volume change, which is given an increment, so 0.1 or 0.03 later. When we see when pad 40 is hit, we increase. Pad 36 is hit, we decrease. And then we make an explicit reference to that. Then we unwrap sort of that reference, and then we pass it to smap of the set rate. So every time this is fired, we set the rate to be either id or the changed value. And then we call run MIDI, which is just a helper function which actually does something with the signal flow. And then we return the reference, which is useful because we're going to want to replace it later. Noticing that it's sort of gradually changing the rate. And I'm feeding a few in here just to make sure that if we were not to be hot swapping properly, it would be pretty obvious. So now I am actually going to hot swap on that value. And just put in replacement instead. And now it should be a lot more drastic, a lot more quickly. So I would love to talk about more possibilities with this, but I'm a little limited on time, so you will have to ask me questions about possibilities about this. Thank you very much. So, questions?
And I think, maybe I will confused about the schedule. I think we actually have plenty of time for questions. Oh, is the schedule wrong? Okay.
Okay, yeah.
Your title is Livecoding Semantics, or so what's semantics?
Sure. So the semantics that I think is crucial to this, to midair, and to the notion in general, is the notion here, is the notion of a pivot where we have, and this is not like a denotational semantics, this is just a semantics. It's the notion that a hot swap on an FRP graph does an update at the point of the change and into the future. And it's the semantics for how we do an update where the past remains as it was, but we have a sensible notion of moving into the future with the new code that we're using.
I would still call it, I don't know, Livecoding extension. That would be semantics.
Sure, sure.
I kind of don't, maybe I missed something, but I don't understand like the live coding aspect of the actually happens. Like you type in an editor and then you can update your single function graph in Haskell from Haskell. Where how do you, if I'm typing stuff into an editor, how do I make that communicate with the Haskell program running?
Sure. So the question was, how does live coding actually happen if we're writing Haskell modules? So there are a couple ways. One is you actually can hold on to your references through a reload. So GHDI is the short answer. So using a REPL, but you can either hold on to references explicitly. There is some new stuff in GHC 8 where you can like the remote ref things, where you can persist references through reloads, so you can reload modules that way, or you can actually just Emacs style send code to GHCI and not actually do a reload. So you're actually as long as you've got the references and as long as you've got a graph. Or could create more graphs, then you're actually able to update anything. And if you want to, do the most drastic thing is every time you call the top level function, which starts a signal flow graph running, you get a node ref to that too. So if you really want to swap out the whole thing, this is sort of your escape hatch. Sorry, there was another question?
Yeah, it wasn't clear to me because of the way you're having to present or contribute to it.
Yeah.
What you were doing. But were you typing into an editor or reloading the program? Were you
Yeah.
were you pressing tabs on the keyboard? Or?
Yeah, so I wish I had been able to make that clear. I actually made this a bit more verbose so that it could, so that what was hidden was actually less. So in the REPL, all that I did was I called change rate, bound the value of this ref in GHCI, and then called hot swap on R with replacement, which is the replacement function.
The first time you were typing into GHCR,
Yes.
you weren't changing any of the Haskell code.
Right. But the more typical scenario is this little snippet here is something that I would be writing as, I'm on stage actually changing things.
So then you would reload in GHCI to manage to persist something.
Or I would have a buffer that I wasn't reloading, but that I was sending pieces of through a socket or something to a GHCI instance.
So is there like a separate thread that you're running stuff to the one that's...
Right now, I was just running from GHCI. My typical workflow actually does both, where I both hold explicit references so I can do reloads, but then most of what I send is strings over a socket to a GHCI instance.
When I tell GHCI to do something, it doesn't give me a prompt again. It's done. That's what I mean.
No, I don't know what you mean. Doesn't it give you a prompt? Oh, sure. Well, all of these actions are not blocking.
So there is a...
So they're not blocking on the music flow.
So presumably there's some concurrency going on there.
Sure. Yeah. You want to be forking your processes, and all the functions which take signal flows can be defined by the user, but a well-behaving one must basically fork its primary process so that you're not blocking.
But you know, a lot of different threads going on.
You could have one. And I think it's crucial that one thing that's really powerful about FRP is that you have a sort of determinism. So in a sense, you don't want several different of these threads firing and sort of racing each other for which effect happens first. What you'd like to have is a larger thing which you can compose, which is actually sort of like the idealized model is you get some sort of MIDI message or whatever your input is or your combination of inputs is. You get it in the top. This big machinery happens in a bunch of places, and you get like this nice sort of combined package of everything that's going to happen sort of spits out the bottom. And that's actually why we don't use I/O, we use FX, because this is like a new type which has a few niceties, including a monoid instance, so you can just sort of like slap a bunch of them together and get them out as one thing.
So...
Why don't we take the rest of the questions offline? We'll move on to the next speaker. But thanks, Tom.
Great, thank you.